Hello, this is Nick Nielsen, and my presentation is Conservation Astrobiology for Spacefaring Civilization. If there is other life in the universe, or something like life in the universe, our relationship to this other life will be one of the great moral dilemmas of spacefaring civilization that would potentially shape the behavior of such a civilization, whether out of enlightened self-interest, as seemed to have been the case with the quarantine of the Apollo astronauts, or out of moral considerations concerning ourselves as moral agents vis-a-vis other life, which latter might also be a moral agent. Even if other life is not perceived as a moral agent, as for example would be the case with extraterrestrial microbes, we as moral agents may determine that we have moral obligations to other life, regardless of whether that other life is a moral agent. On the one hand, the existence of other life is something that we would want to study for its value to scientific knowledge, and thus the very possibility constitutes a strong draw for us to explore the cosmos. On the other hand, the potential impact of other life upon us, or our potential impact upon other life, may entail limitations to the human exploration of the cosmos. These potential moral forces shaping a spacefaring civilization may be encountered as close to home as Mars or the subsurface oceans of the outer solar system moons, which means that debates over these risks and opportunities will shape our immediate future. To date, the concept we have come to employ for these discussions is that of planetary protection. The NASA Planetary Protection Independent Review Board final report of 2019 summarizes planetary protection in this way, quote, planetary protection refers to 1. Managing contact between terrestrial life forms and organic material from celestial bodies as it relates to adversely affecting the scientific study of these bodies, called forward contamination, and 2. Mitigating harmful contact between pathogens or biology from other celestial bodies and terrestrial biology, called backward contamination, end quote. The recognition of the problem can be dated back at least to 1958, when Lederberg and Cowie wrote in the science paper titled Moon Dust, quote, since the sending of rockets to crash on the moon's surface is within the grasp of present technique, while the retrieval of samples is not, we are in the awkward situation of being able to spoil certain possibilities for scientific investigation for a considerable interval before we can constructively realize them. We urgently need to give some thought to the constructive measures needed to protect scientific objectives on the moon and other planets, end quote. The same year, 1958, COSPAR, the Committee on Space Research, was founded, which took an early interest in planetary protection and continues today to actively formulate planetary protection protocols, often in partnership with NASA. But whereas Lederberg and Cowie formulated their concerns exclusively in terms of the potential threat to scientific knowledge, as the idea of planetary protection gained currency, it also shifted from a focus on scientific knowledge to a focus on contamination. The COSPAR Planetary Protection Policy of 2002 quotes DiVincenzi et al. As follows, quote, the conduct of scientific investigations of possible extraterrestrial life forms, precursors, and remnants must not be jeopardized. In addition, the Earth must be protected from the potential hazard posed by extraterrestrial matter carried by spacecraft returning from another planet. Therefore, for certain space mission / target planet combination, controls on contamination shall be imposed, end quote. The idea of planetary protection formulated primarily in terms of contamination suggests a fortress Earth mentality, which is essentially a geocentric idea. And this fortress Earth mentality may be extended to each world harboring life or something like life, so that inhabited worlds are not merely an archipelago of life in a sterile cosmos, but a chain of isolated fortresses, each individually sealed up within its own pristine biosphere. But astrobiology does not suggest this picture of life in the cosmos. Astrochemical studies have shown us that the elements of life are present throughout the observable universe, and Origins of Life Science has shown that rudimentary organic molecules will appear where the conditions for them obtain. Furthermore, exoplanet studies now suggest millions of worlds within our galaxy alone upon which the conditions may be right for life. If life is pervasive throughout the cosmos, as these observations imply, then life in a cosmological context, as studied by astrobiology, is not the exclusive concern of Fortress Earth or Fortress Mars, but the cosmological landscape within which these worlds evolved. Lithopanspermia may communicate life between worlds within a given planetary system, and there may be more exotic vectors of transportation for life that we cannot yet imagine, such as would enable the dispersal of life on interstellar scales and perhaps also on intergalactic scales. For example, on cosmological timescales, planetary systems pass each other as they circulate within the galaxy. Other planetary systems have passed by our solar system many times since Earth evolved a biosphere, and in the time remaining for the terrestrial biosphere, more planetary systems will pass within less than a light year of our solar system. Even if lithopanspermia is effectively limited to the distances typical of a planetary system, this limitation would not necessarily limit the transmission of life to within a single planetary system. Also, when planetary systems pass near each other, the unpredictable gravitational interactions between the two planetary systems could cause an exchange of planets or other bodies, and if these planets or other bodies harbored life, that life would then be transferred from one planetary system to another. Perhaps a more humane way to think about the problems that planetary protection casts in terms of contamination, and perhaps a mode of thought more appropriate to a spacefaring civilization expanding its knowledge of the cosmos into which it expands, is that of conservation astrobiology, which we can formulate from the conjunction of the concepts of conservation biology and astrobiology. We have, firstly, the scientific framework of astrobiology as a discipline for the study of life in its cosmological context. The NASA Strategic Plan of 1996 gives this definition of astrobiology, quote, the study of the living universe. This field provides a scientific foundation for a multidisciplinary study of 1, the origin and distribution of life in the universe, 2, an understanding of the role of gravity in living systems, and 3, the study of Earth's atmospheres and ecosystems, unquote. The NASA Astrobiology website characterizes astrobiology as follows, quote, astrobiology is the study of the origin, evolution, distribution, and future of life in the universe, end quote. The most concise definition I have found for astrobiology is this. Astrobiology is the study of life in the universe. Astrobiology is a recent science, and so too conservation biology is a recent science, and indeed a science that can be dated to the second conference on conservation biology in 1985, and a paper from the same year, What is Conservation Biology by Michael Soule. Soule defined conservation biology as follows, quote, conservation biology, a new stage in the application of science to conservation problems, addresses the biology of species, communities, and ecosystems that are perturbed either directly or indirectly by human activities or other agents. Its goal is to provide principles and tools for preserving biological diversity, end quote. Drawing on these definitions of astrobiology and conservation astrobiology could then be defined as follows. The application of science to conservation problems in the study of the living universe, or the application of science to conservation problems in the study of the origin, evolution, distribution, and future of life in the universe. The point here is to draw upon existing conceptual frameworks, specifically those of astrobiology and conservation biology, so that we do not need to reinvent the wheel in our effort to come to grips with the ideas and the conflicts that would inevitably follow the further development of spacefaring civilization. For example, J. Baird Callicott makes a tripartite distinction among 3 traditions in conservation ethics, each of which could be transposed into the context of conservation astrobiology. The Romantic-Transcendental preservation ethic of Emerson, Thoreau, and Muir, in which the human presence in nature is an experience of edification that tends to moral improvement, in the context of conservation astrobiology, becomes the preservation of pristine planetary biospheres for the moral edification of agents that might otherwise plunder these worlds for short-term gain. The preservation of worlds in their natural state of wilderness would be, on this interpretation, a spiritual benefit for all of us. The pragmatic utilitarian resource conservation ethic of Gifford Pinchot entails conservation in order to justly distribute natural resources among multiple generations and to avoid the waste of natural resources, which are to be exploited efficiently for the benefit of all. The resource conservation ethic adds the important element of intergenerational moral duties, which expands the scope of our concerns even if we favor the exploitation of natural resources for exclusively human aims. We can then also expand the spatial scope of resource conservation so that it applies to multiple worlds over multiple generations, all of which have some claim to these resources. In the Evolutionary-Ecological Land Ethic of Aldo Leopold, nature has intrinsic value, not merely in not merely in edifying observers or meeting practical needs, and evolutionary and ecological processes have an integrity of their own that must be respected. Moreover, human beings and presumably other intelligent agents are a part of these evolutionary and ecological processes, so that our own integrity is part of the integrity of nature, and the integrity of nature is part of our own integrity. In a cosmological context, this becomes a recognition of the intrinsic value of the cosmos and respect for the integrity of natural processes that generate biospheres. As these arguments have all been made countless times, and arguments against them have been made countless times when applied to particular ecosystems on Earth's surface, we need only scale them to cosmological dimensions to see the obvious ways in which such debates would play out in an astrobiological context. There are, of course, already intimations of conservation astrobiology within astrobiology itself. The NASA Astrobiology Roadmap of 2008 lists planetary stewardship as the second of its 4 basic principles of astrobiology, but in doing so uses the language of planetary protection. Quote, astrobiology encourages planetary stewardship through an emphasis on protection against forward and back biological contamination and recognition of ethical issues associated with exploration, end quote. Another intimation of conservation astrobiology can be found in the attempts to grasp the planetary scale of the Anthropocene. E.O. Wilson, in his book Half Earth, Our Planet's Fight for Life, suggested that in order to adequately address the biodiversity crisis, we should set aside half of Earth for conservation. Wilson's half-Earth proposal demonstrates conservation thinking on a planetary scale. Conservation astrobiology represents conservation thinking on a cosmological scale, but for us, this will first mean conservation thinking within our solar system, which means expanding our conservation thinking from Wilson's planetary scale and extending this to other planets and moons of our solar system, conservation thinking on a multiplanetary scale for a multiplanetary species. Suppose we find life on Mars in the form of subsurface microbes. A biosphere of subsurface microbes would likely represent far less biodiversity than the luxuriant biosphere of Earth, but there would still likely be some variation in the subsurface biosphere among Martian regions, and we would want to carefully choose what conservation areas should be set aside to ensure the continuity of Martian life. Suppose we set aside half of Mars, as Wilson has suggested that we set aside half of Earth. How would we go about determining what half of the surface area should be preserved in its pristine state? To answer this question scientifically, we would need to conduct a full biodiversity survey of Mars, and we would have to understand the ecology of Martian ecosystems in order to determine how they function in relation to their planetary environment. All of the extraterrestrial environments in our solar system would pose unique challenges that would differ from the challenges of terrestrial conservation. The global subsurface oceans of Europa and Enceladus would probably have to be set aside entire, as the conservation of half of a subsurface ocean may be an ineffective conservation strategy. If many of the subsurface oceans in our solar system have evolved life, and each of these instances of life are distinct, for the purposes of scientific knowledge, we would want to study each in their pristine state. As long as they held no resources coveted by human beings, this would not present a difficulty. But if valuable resources are to be found in these subsurface oceans, for example, if water itself is a valuable resource in the outer solar system, then the stage is set for a conflict between the preservation of distinctive ecosystems, both for scientific knowledge and for their intrinsic value on the one hand, and on the other hand, human demand for a resource. These problems cannot be wished away, but they can potentially be managed. If it becomes a matter of determining how much water can be taken from these moons without compromising subsurface ocean biospheres, conservation astrobiology will be the discipline that will be called upon to make this determination. Thank you.